Last time we started with curve fitting. Okay, so now let's continue with the topic. First is curve fitting with a linear equation wherein the equation is a first degree polynomial y equals a1x plus a naught. Okay. And we also discussed that we aim to minimize the residual or the difference between the true value and the value from our equation. So you can uh, imagine the residual as this, the distance of the true values from the f of x of our equation. Okay, so we can say that the overall error is the summation of the residual. Okay, wherein it's since residual is the difference, so yi minus the equation a1xi plus a naught if your equation is a linear equation, first degree polynomial. Okay, now a definition for the overall error that gives a good measure of the total error can be used for determining unique linear function has the best fit is obtained by making the e equal to the sum of the squares of the residual or the error. So e is equal to summation of ri square, or simply we just have to square the equation earlier. Okay. Okay. So let's focus on linear least squares regression. So this is widely used in curve fitting. I think this is the first approach, no, in determining your best fit line or determining the equation of a line that will fit your given data. And in fact, if you proceed with machine learning, you you will come up with the same concept, no? Because in machine learning, uh, they are predicting, right? They are predicting the values from a given sets of datas. Okay? And in machine learning, the datas are in thousands. No, it has a lots of datas. No? Therefore, you will deal with matrix, and it's the same concept. You will need to minimize the error or the sum of the squares of the error. Of course, if you are dealing with minimization, we are finding the partial derivatives. Okay, for example, here I have here a derivation of that. This one. So linear least squares regression. Okay, remember e equals to this equation. Okay, and then taking the partial derivatives. Okay. So that means dE over dA naught. So if we perform this, dE over dA naught, okay, if you perform this, we will have, okay, that means A naught is our variable, no, the rest are constant. Okay, so 2 will be transferred here. Okay, that's why we have this. Okay, and then this equation will be intact here. Okay, a naught is simply derivatives of a naught is 1. So this is the equation we got. Okay, now if you expand this, you will come up with this, right? Negative 2 summation yi plus, because this is negative and negative, so that will be positive 2a1 summation xi. Then negative times negative, you have positive 2 summation a naught. Okay, so this is the expansion. Next is, let's minimize with respect to a1. So dE over dA1, same procedure, 2 will be here. Okay, then this one is intact as here. But what's the derivative of this whole thing with respect to a1? So x sub I. That's why we have x sub I here. Okay, and again, expand this, you will have this. Right, so negative 2 summation yi xi, because we have xi here. Then negative times negative, positive 2. Okay, positive 2 a1. Okay, then summation xi. Since you have xi also here and another xi here, that will be squared. Okay, and negative 2 times negative a naught is positive 2 a naught, summation of xi. Okay, so that's the expansion. Maybe I'll write expand. This one is here. Okay, next is, so we got two equations, two unknowns, right? You have a sub 1 and a sub naught. So that's the two unknowns. And then if we rewrite this two equation, two unknowns, you will come up with this. If you rewrite this whole thing, come up with this, right? Summation xi a1, that's one. Okay, and then since 2 is constant, now we can write this as this. Okay, and then summation yi, 2 is also constant, that's here. Okay, and then 2 is common in all terms here. Okay, then for the second equation, yixi is here. Okay, so it was this is transposed to the other side. Xi squared a1, xi squared a1, this one, and a naught summation xi is this one. Okay, so two equations, two unknown. We can solve this by Cramer's rule, right? Wherein we can express this in matrix form. Okay, maybe in matrix form, that's it. This whole thing is expressed as this. Okay, I forgot the maybe I forgot to write down the unknown coefficients. Which is a naught and a1. a naught a1. Okay, so n a naught plus summation xi a1. Okay, so in Kramer's rule, basically if you're finding a naught, what did he get first? A1. He gets first a sub 1, a sub 1. Okay, a sub 1. So we will replace this second column here by this column, right? And find the determinant. That's why this one is replaced by this one, which is here. Okay, and then this is intact. Okay, then find the determinant. So the determinant by to get the determinant, n times this, so n times summation xy, then minus summation xi summation yi, right? So that's your numerator. Okay, so this determinant is your numerator. Okay, and this one is that's it. It's your numerator. So n summation xy minus summation xi summation yi. Then to find your denominator, simply find the determinant of this. Okay, so which is, so I rewrite this here. Okay, n summation xi summation xi summation xi squared. Okay, so n times summation xi squared, so you have to multiply this here going down, n summation xi squared, then multiply this from here to here. Okay, summation xi, since they are both summation xi, that will be squared. So that's it. This whole thing is your denominator. Okay, so that's your a sub 1. So to get a sub naught or a0, so same procedure, but this time you will replace this first column by this column. Okay, that's why you have this. This column will be your first column here, and this is intact here. Then find the determinant. So that's your numerator. yi xi squared. Okay, then xy times summation xy. Okay, minus. So that's your numerator. Okay, yi xi squared xi xi yi. Okay, and your denominator is still the same. Okay, summation xi squared minus summation xi, then overall square. Okay, so that's it. So, and we again rewrite, or so to simplify the equation such that summation xi will be called sx, all summation yi will be called sy, summation xiyi will be called sxy, and summation xi squared will be called sxx. Substituting that, you will have this equation for the coefficients a1 and a0 for a first degree polynomial y equals a1x plus a0. Okay, so if you, so this we have this sample problem here. Okay, I'll discuss that later. Okay, so curve fitting with nonlinear equation, again you'll just have to transform the non-linear equation into a linear form. Okay, so for example, y equals bx raised to m. Apply, find the natural logarithm on both sides. We'll come up with this. Okay, what if you will deal with a higher order polynomials? Okay, so like this. So there's a derivation again here. Okay. 1. Okay, so that one. Okay, but let's generalize that. Now let's generalize that. I have here is minimize. Okay, so to generalize that procedure, so we have here another approach. Okay, so still method of least square, okay, and then so still the formula for residual is this, no? We aim to minimize that summation of ri squared, wherein r is simply the yp minus y1. Okay, so minimize that with respect to the each coefficient. Okay, so summation d summation ri squared over dc1 will be 0. Since this is square, bring down 2 here, ri, then find the partial derivatives. Okay, so if you are finding the partial derivative with respect to c1, this is also c1. Okay, and then this is dri over dc1. If you are taking the partial derivative with respect to c2, this is still dc2, and this is dri. Let's expand that. Right, so by expanding I here, so we have r1 dr1, right? If this is 1, this is 1 also. Okay, so r1 dr1 here. Okay, r2 dr2, right? Still, if you're in dc1. So on until you get r sub n dr sub n dc1. Okay, good here. And then let's generalize if dri over dc sub k. So for example, they have different numbers. Okay, if you are trying to find the partial derivatives of the residual 2 over dc5, the unknown coefficient, the c5. So write down the original equation here, c1 f1 x sub 2 plus c2 f2 x sub 2. Okay, and remember, in this partial derivatives, only c5 is the variable. Therefore, if this is a variable, this one will be your derivative. So therefore, the answer is this, f5 x sub 2. Okay, because everything else are constant. No? Okay. So in general, dri over dck is fk x sub I. Okay. Next. So we can, in matrix, now we will now transform everything into matrix. So where is the So we will transform this, right? So let's transform this in matrix. So we have this, right? So R1, R2 up to Rn multiplied to dr1 dcn dr2 dc1 dr1 or dr1 over dcm. No, sorry. So this is row to column, sorry. So dr1 dc1 here, next here, the next value here, dr1 dc2 dc1 up to dr1 dcm, which is here, right? Okay, so we just transformed everything here into matrix as this. Okay, so equal to this matrix 0. And remember, that's why we generalize this dr1 over dri over dck. So this matrix is equal to this. Because that is dr1 dc1 okay. Now let's name this row matrix or row vector as R, and let's name this as F matrix. Okay. And transposing so if you transpose these two matrices, they will interchange, right? So we have this, they interchange, since R1 R2 column matrix is equal to this minus, sorry, this, we can rewrite that as F transpose remember this is F basically this C coefficients here are this matrix, okay, and then this F sub x, remember this F of x are the F matrix, so this is F, okay, minus this, which is this, okay, because this one or this one is equal to this. Okay, so F transpose intact here, then our vector is this whole thing here, the right side here, which is this one, equal to 0. Okay, so therefore distributing F transpose times F, then the C unknown C coefficient is equal to F transpose, I'll clean this, So F transpose times F times C, which is this one. Then distribute this first, F transpose here, and then transpose to the other side. So that is your equation. Or in general, F transpose F, then the C matrix of the unknown coefficient is equal to F transpose the Y matrix. So these are given, no? This is given in your experiment, in your data sets. Okay, the observed values. Because we're trying to find this. Okay, so that's just a general approach in matrix form. So basically, if you did this in our previous derivation, you will come up with the same answer. Okay, we just generalize everything in matrix. Okay, so with this method, we can now apply this in a spreadsheet. This one. This one. So general linear least squares regression up to this spreadsheet is up to x raised to 4 or 4th degree polynomial. Okay. So if you will check the formula in finding the C coefficient, this one, and compare this with what we derived here. See, so we are basically finding the transpose of the F matrix, okay, and then multiply to the F matrix again, M mult, then multiply the transpose of the F matrix to the F matrix itself, which is this one. Okay, and then since the unknown coefficient C matrix is here, therefore we will have to transpose, or sorry, to divide this encircled matrix here, which is inverse. So that's why we're finding the inverse of this F transpose F. And then after finding the inverse of that, we will again multiply that with this one, the transpose and the observed Y values, which is this one. Okay, so that's why I teach this general approach in matrix form. Okay, so first problem is the one in our book. No. Okay, so for the first problem, so I have this here, this one, sample problem. We have given data points 1, 2, 3, 4, 1, 3.8, 2.5, 15, 3.5, 26, and 4, 33. So I'll be, I think this is the one here. I'll minimize this. Okay, as a disclaimer, this is I also got this spreadsheet in Google, no? Sometime maybe 5 years ago. Okay, so we have observed points 1, 2.5, 1, 3.8, 1, 3.8, 2.5, 15, 2.5, 15, 3.5, 26, 3.5, 26, 433, 433. Now the instruction is indicate a y equals c1 plus c2x squared relationship. Okay, of course, then find the value of c1 and c2. Okay, so this is the manual solution, no? Or handwritten solution. So we set again, this is the F matrix, okay, which I explained earlier. So in this case, F1x is 1 because yeah, because you have C1, therefore your F1x is 1. So to make C1 as itself, okay, so here this is this column here will be 1. Then since we are instructed in this equation C2x squared, therefore F2x will be x squared. Okay, so F2x here will be x squared. That means all x's will be squared. Okay, so if you go down here, okay, set this up, so our F matrix will, from this general matrix F, will become a 2-column matrix F, because our equation is only consisting of 2 unknown coefficients. So F1x, F2x1. So set up this one here. Okay, so all x's are squared. Okay, next, F transpose. Remember, this is our equation. We need to find the F transpose. So this is the F transpose. Then find F transpose F. Okay, as in our general equation. F transpose F, then the C column matrix, unknown column matrix, is equal to F transpose, then the Y matrix, the observed values. Okay, so write down everything. F transpose times F times unknown C is equal, so F transpose is this multiplied to the Y values. Observe. So basically you have one equation, one unknown matrix. Okay. So performing this one, so F transpose times F is this values. Okay. Then F transpose times this matrix is this value. Remember, you have this is 2 by 1, 2, 3, 4, while you have 4 by 1, so compatible. So you will get a 2 by 1 matrix, which is this one, 2 by 1. Okay, that's it. So C1, C2 is this. Now therefore the equation is Y is equal to C1 2.27 plus C2 1.93 x squared. Okay, so this is the implementation in matrix. So in our spreadsheet. Oops. Minimize this. So I simply here, okay, plot the datas, and you can now choose, no, what relationship you wanted, no? So since the problem instructed us a 2, no, C1 and C3, no, we will activate C1 and C3 x squared. Okay, that's why I have here, this is the x squared, and this is for the C1. So I have to make another matrix. Okay. So this is my, call this F. So this is my F matrix. F matrix, right? So see, this is my F matrix. Okay, then of course you need to find the F, the transpose of this. Then where is my this Y? Observe is this one here. Okay, so next is N. Okay, so this is my equation. So So implementing this matrix formulation. So highlight this and look at my formula. Okay, so I transpose C3 this range, our F. This is the finding the transpose of this, and then multiply to itself, to F matrix. Okay, the transpose times the F matrix, then finding the inverse of that, because that will be here, then multiply to the transpose of the F again. Okay, F transpose times the Y. My Y matrix is basically this one. Okay. Okay. And so performing that, I have this answer, getting the C unknown coefficient matrix. Oops, which is this 2.27 and 1.93. Okay. Okay. So next is problem number 2 in our book. Problem number 2 is absolute temperature. That's absolute temperature. Absolute zero temperature. This one. So determination of absolute zero temperature. So if you will see, I plot these datas. So the observed is this column 0.94, 0.96, 1, 1.05, 1.07, 1.09, 1.14, 1.17, 1.21, 1.24, 1.28. So that's our Y matrix. Okay. And what's the required linear least square regression? Just a linear, no? A1t plus A naught. Okay, it's a linear equation, so we only need C1 and C2. Okay, so C1 and C2, which is so this is our F1 and this is my F2x. If you notice, it's simply everything, all x's. Okay, no need to square because we're just finding a linear equation, first degree polynomial. Okay, but of course, I need to create again my own column matrix here for F. So this becomes my F matrix. Okay. So if you will observe earlier, our first problem is second degree, no? So I utilize this. For this problem, we are only required for a first degree polynomial, so I utilize this. Or to segregate that, this is my F matrix, and this is my Y matrix. So simply by doing the same approach, so highlight this and then look at my formula. See, again, F transpose multiplied by F, this one, then get the inverse multiplied to the F transpose again multiplied to the Y column. So you will have this. Okay. So I got 0.933, 0.003. So what does, so it has, okay, so using the derived formula we derived earlier, no? So he got 0.003345.9428. So very almost the same, no? 0.9428 as the unknown coefficients. Okay, but in our book, reference book from Casimali, he has a MATLAB code. So implementing that, he obtained this, which is almost the same with our spreadsheet. Okay. So again, just by implementing this general formula. Okay, this general formula here. So this is our C. Okay, so next problem is, or last problem is a sample stress strain. Stress strain is higher order polynomial. So strain is in the X. Take note, no, by the way, no, you might get a numerical error. So in order to inverse, no, because we will be inverting matrix, I assumed a very small 0.0001, because if you input exact 0 here, you will get a numerical error. Okay. So same with this problem. This is my spreadsheet here. It's not exactly 0. No? If you see, there's a very small numbers, no, need to be typed in. Okay, so for this problem, we are required for a fourth order. Okay, so we will be using this whole matrix. Okay, this whole matrix here in the spreadsheet, because we are now getting a fourth order fourth degree polynomial. And if you type in all this data, so 0, 0, 0.43, 0.43, 0.8, 4.5, 1.2, 5.8, 1.6, 5.9, 2 and 5.8, 2.4, 6.2, 2.8, 7.4, 3.2, 9.6, okay, so on and so forth. Okay, and then so that's your F matrix. This is my Y matrix, so which means now complete. So this is your F matrix here, and this is your Y matrix here. Okay, we are finding the C matrix unknown coefficients, which is this one. So up to 5, C1, C2, C3, C4, 5th, because of fourth order. Okay, so that's it. Transpose of F multiplied to F, then find the inverse because it will be transferred here, then multiplied to F transpose and the Y matrix, this one, to find this. So C is this 0.2756, 12.8799, negative 10.1938, 3.1188, negative 0.2644. So which is this. So this one is solved using MATLAB. Okay, 0.2644, 3.1185, 3.1188, negative 10.1927, negative 10.1938, 12.878, and negative 0.2746, 2756. Okay, so that's it. So that's how you're going to implement a least squared method, no, in spreadsheet, which is derived using this this procedure we discussed earlier.